Okay, we are live. I'm going to record because I didn't get to the other class.
Okay.
So we are going to look at 6.3. So far, we combined polynomials with a couple operations. How did we combine them? We did what? We subtracted them. We added them. We multiplied them. So logically, we should know how to divide them. So this is dividing polynomials. There's two ways to divide polynomials. We're only going to learn one this year. It's called synthetic division. I think you'll like it. It's just a little new algorithm that you've never seen before. It's pretty quick. It's not hard to use. It is limited. So the other kind of division, what's a division you learned way back in elementary school you probably didn't like very much? Long division. You can divide variable expressions with long division. In fact, I think it's easier than with numbers, but you can make mistakes with it. It's kind of more powerful, but this is a lot faster. So we're just going to learn this year. It's almost all you ever need. You need long division once in a while, but it's good enough. Okay? So how do you divide this polynomial by that one? So I'm taking a degree 4 polynomial and dividing by a degree 1, right? There's the 1 right there. Or in other words, I'm dividing a 4th degree by a line. Does that make sense? Here's the limitation, and I'll put this right away because I forgot to tell the other class this. They kind of came up with it on their own. But synthetic division is limited, or we'd always use it. It's limited to dividing by lines, dividing by linear polynomials. If I wanted to divide by another type of polynomial, I'd have to use long division, okay? And I could show you how to do that. Maybe we'll do it another day if we have time. It's kind of fun, actually. I like it. It's neat. It's better than regular long division. But anyway, how does it work? So, new algorithm for us. So first, we do this little thing over here. I'm just going to draw. Okay.
Every problem starts out like that?
Yep. If you're going to divide, this is how synthetic division looks. This is the machinery. And you take the opposite of the linear term, so it's kind of like transformations almost. The opposite of 2 plus 2 is going to be minus 2. We'll think about why that is as we finish this chapter, okay? Right now we're just going to accept it. It's kind of like we're plugging in the 0 that corresponds to that factor, doesn't it? Because that's the 0 that corresponds to that factor. That's kind of why we're doing this, and we'll see in a couple days how that works more precisely. Anyway, then we take the coefficients from here and write them down. So the first coefficient is 3, and then
1.
or negative 1, and then
5.
nope. What's next? It's not 5. It's not negative 1. It's not 1. 0, Sarah. Why?
Because there's no x squared.
There's no x squared term. And if you remember back to when you were in elementary school, did place value matter? Like especially when you were doing division? Did it matter like where you put zeros and stuff? Yeah, I think it really mattered. So this is just like that. You need to make sure you keep your place value. This is the x squared place, isn't it? We could even put it in there if we wanted to. We could say plus x, 0x squared, couldn't we? Okay, so if you're missing anything, you need to put zeros in. That's the only tricky thing to synthetic division. It's a thing people mess up sometimes, okay? Something's missing, it needs a 0. And then we have, what's next? And then, okay. So now here's how the algorithm works. Long division has a minus, this has a plus. Always write down your plus so you don't forget you're adding. I want another red. Anyway, you bring down the 3. You multiply by the 0 thing we had up there, which is what? Negative 6. And then we add, so and then you repeat. So you say positive 14, and you add, and you repeat.
Oh.
And that's what? Negative 28. I kind of smashed this together too much. See, I like to leave a lot of space between these. There's my 5, there's my negative 1, okay. And then we add, what's that if we add? So negative 23, and you repeat, and that's going to be positive 46. And you add, and you're done. So now the only question is, what does all that stuff mean down there? So that's what I'm going to tell you. Okay. We're going to do it again. We're going to do a couple. So what is this stuff? This is the quotient and the remainder. Sometimes there's not a remainder. So where is the remainder in this thing? It's the last thing always. So you just always put a little guy right there to quantify the remainder. And you say, here's what I did. I found that the 4th degree polynomial, this guy, this is never, you're never going to see this in the future. What you will see is divided that way, yeah? We'll see it a bunch this year too. That guy divided by that guy, that's what that says, right? And what's it equal to? Well, we've got our answer right here. What's the quotient? So the quotient's this part. So we say 3x to the what, do you think? Any guesses? Well, what did it start out as? 4th degree. We divided by degree 1, so we're left with degree 3. If we just wrote that like this, wouldn't it be like this if we just kind of looked at the first things? What's that cancel to? Doesn't it become 3x to the 3rd? Okay? And then we got to finish. So what else is left? Minus
7 to the x to the 2nd.
Plus 14, and you just walk down. So there's the quotient. If you divide that one by that one, you get a degree 3 polynomial. In fact, this one, but we have something else too. We have a remainder. How do remainders work? Technically, do you remember? Let's do a simple long division problem to remember remainders. Yeah, so what is 80 divided by 9? Let's see if we can do that. How many times does 9 go into 80 evenly? 72, right? So we go 72, and then for that we subtracted, right? We went like 8. So the answer to 80, I'll write it over here. The answer to 80 divided by 9 is, how many times did it go in? 7 times. That's the quotient, and the remainder was 8, but if your teacher just told you to write r equals 8, that's bad.
9 times 8 is 72, not 9 times.
Thank you, Logan. You were correct. But we still get an 8 here too, right? Okay. Anyway, thank you. So we get a quotient of 8, and the remainder is 8. But it's not just 8. It's 8 whats? 8 ninths. So your teacher, if they're a good one, would have told you to do it that way. Well, mine didn't either. So 8 plus 8 ninths. Does that make sense? So then for us, what are we going to do with our remainder? We're going to put, well, it's positive. So it's positive. No funny business. 45 whats? Yes. 45 of those. Yeah? It's the same principle.
That's always the last one?
That's always the remainder, yeah. And if the last thing was 0, then it went in evenly and there is no remainder. We'll talk about that more.
If you put it in your calculator, we'll get
No way. Calculator can't do this. We're going to use the calculator as much as possible, though, believe me. Otherwise, stuff like this would be much more painful. Let's see.
Oh.
Let's do another one. Okay. Yeah, I don't think this one's too bad though. All right, so set it up. You guys help me a little bit this time. I think we need to do it one more time together for sure. What goes here? The 0. What's the 0 for that linear term? It's not negative 1/3. It's
1/3.
Oh, right.
It's 1/3. Okay. And this is just a process, right? We're only learning a process here. This is one way to divide stuff. The Arabics came up with this. I forget which Arabic scholar in like the 11th century came up with this. If you did it the way that it was done before those guys did it, it's so terrible. Like it takes pages to do things like this. So this is a very condensed, nice algorithm that was developed in the 11th century. Okay. Anyway, it had all kinds of funny language because it's in Arabic, right? But anyway, 1/3. What goes here?
3. 9.
We didn't skip anything that time, so we don't have any zeros, right? If there's like more stuff at the end that's skipped, put zeros. Okay, then we do our algorithm. Plus, bring it down. What's 1/3 times 3? 1. 9 plus 1 is 10. Oh, this isn't going to be super nice. 10 times 1/3 is 10/3. And then we're going to have to think a little bit here. That's going to be the remainder, right? So then off to the side or with our calculator, I'd encourage you to try to do it as much as possible without one. But you could just type this right in your calculator and it'll give you the answer, won't it? Should we do that real quick? There's a few fractionally impaired people.
It's hard to know.
You have
Okay, so on the calculator I would type in -2 plus 10 divided by 3. Might want to put parentheses around that if you're worried. Enter. I don't want that though. How do I get fraction? Math. Fraction. Here it is. 4/3. So that's the easy man's way out, but it doesn't help you for learning stuff later on. So, but if you have to do it that way, then you'll have what you need. For us, we're going to think common denominator. What's the common denominator of these two things? 3. So we need to make this into thirds. How many thirds fit into 2? A whole bunch of them. Isn't it 6/3 that fit into 2? So -6/3. What's -6 and 10? 4/3. There's the calculator's 4/3. Okay. So let's write out the answer. That's key. All these, I want to see this written out just this way.
3x plus 10. 3x.
3x, right? One less than that was. This one is.
Plus 10.
Plus 10.
Plus 4/3 over x minus 1/3.
Plus 4/3 over x minus 1/3. That looks weird, but it's okay. There's all kinds of reasons to divide polynomials like this. My calc class, like next week, is going to be using this. They will be confronted with things like this that they have to use in calculus. I'm not going to tell you what they're doing with it. But it's really hard for them to do it when it's in this form. If they change it to this form, even though this thing over here looks scary, it's like super easy. It's like do it in your head, it's done. Okay? So very important stuff we're learning here. Anyway, we could do one more if we have time. I don't know though. Let's see. One last thing.
Make it too hard.
What's called the remainder theorem is in this section because it has to do with synthetic division. So you have a couple of those. So the remainder theorem says this. I'm going to go informal. I don't know. I'm making it up. So this is what the remainder theorem tells you. If I was being real particular, how would I phrase a theorem? I'd say if blah, then other blah, right? So I'm doing this very informally. I'm trying to tell you what it means mainly. Okay, so another way to find just the remainder when you divide, like, you can tell it's very formal. Something like that, isn't that what we've been doing? We've been taking some polynomial, maybe I should call it P, how about that? P for polynomial. And you divide it by a linear term, isn't that what we've been doing? So it says another way to find just the remainder. If you only want the remainder, there's a really easy way to do that without synthetic division, if you like. Is to compute P of C. Just stick C into P, and you'll get the remainder. If that's all you care about. If you need the quotient, if you want this 3x plus 10 thing, this really can't help you, okay? But if you just want the remainder, this will do the job, and it's easier probably than synthetic division. You can do it either way. Synthetic division is pretty fast too. It's kind of up to you. It's a judgment call, okay? This is important, we will see in the next couple sections, because there's another theorem that's real brief like this called the factor theorem. If you get 0 for your remainder, what's that mean? What are you going to be adding here? 0, so you're not going to be adding anything. In other words, this thing would be a factor of that thing. Does that make sense? We know how to factor things like this, right? Like x squared minus 2x plus 15 equals 0. Can we factor that? Sure, right? Linear functions are factors already, so you don't have to do anything with them. Yeah? What if you want to find the zeros or factor something like that? Is there like some new method that I'm going to show you for each new one? Like, is it different for degree 4 and then degree 3, and they all have their own factoring techniques and stuff? The answer is no. All you need is synthetic division, and you need to be clever. So that's where we're going in this chapter. The ultimate goal of this whole chapter is to be able to take any polynomial, find its zeros, draw it, do anything with it. And it turns out that's not actually that hard. We're going to make use of little things like this, okay? So if we were like doing this polynomial and we divided it by x minus 3 or something, and it came out to be 0, then we'd say, hey, x minus 3 is a factor, and then we could like try to factor it a little bit. That's what we'll do. Okay? There's the big idea of the whole unit. Question?
What if it goes like x squared, x to third, x squared, but doesn't have x or...
Okay, good question. So I know everyone's going to bring up this because it's like the second problem you're going to do. It says like something, what if you had like this kind of a problem? And that's all you had, and it said divide that by x minus 5. Let's just write that out. So we put what here? 5. And we put what here? Okay, 1.
0, 0.
0 for 4.
0.
0 for 3.
1.
1 for 2. Is there anything here?
No.
0 for 1 and 0 for constant. Okay, so things like that might have a lot of zeros. You might have a couple that have stuff missing at the end. If you don't do that, you're going to get an answer that doesn't make sense. It'll be like, okay, something's wrong here. Okay? All right, that's it. Oh, before I stop the video, so the assignment is pretty short. It is 426, 19 to 29. Okay? The directions, there's two kinds of problems. The directions on the second one are bad. So for 25 through 29, I just want you to compute the remainder for whatever thing they give you and tell me if it's a factor or not. That's it. So is the remainder 0 or not, I'm asking you. Okay? Those will be really easy. Ignore their directions. So compute the remainder however you want. There's 2 ways to do it. And tell me if it's a factor, that's all.